So this is example number 2 on potential flow basics. In this example, we have three scenarios. We have double donuts that have a flow around them, a circulation. We got two identical airfoils and have a circulation around them and a big circulation around the whole thing and have a point P. And then we have a case number 3. We got a circulation around the airfoil and outside circulation around the circulation A that has the airfoil, and I have a circulation C. And what we want to do is we want to identify this particular problem if the loops are reconcilable or they're reducible. Okay, and then the next thing we want to do is we want to see if the loop C, there will be this loop around the double donut and the two element airfoils of these two. If the we want to determine what's the value of that circulation loop. Then the next thing we want to do is we want to see if what is the circulation of this loop, okay, the circulation of this loop around this airfoil. The last thing they're asking is give a suggestion of the possible values of a potential, velocity potential that can be located at here if P is actually has a value of 1. Okay, so the first thing we want to do is let's go ahead and review very quick. Let's do one item at a time and let's review very quick what are the definitions. So the definitions in the problem, we know the definitions of a reconcilable loop is one where this is definition. Any two circuits in a connected region are reconcilable if they can be made continuous variations without ever leaving the region. Okay, let's see. Can these two become one without leaving the region? Actually, no, because if these two become one, now this loop will contain this region and this region. So that's not possible. And same thing here, right? So let's go for this case. So here it's the same thing. I cannot reconcile these two because if I do this, I'm going to have to combine these two. And if I combine these two, now this loop will have this one as well. So it's going to leave the region. It's not possible. The only possible option that we have here is this A and B can actually be reconciled. Why? Because if these two join together, then we'll have just one airfoil and neither one of them leaves the region. Okay, so what I can do is no loops are reconcilable except A and B for to the airfoil. That would be figure 3. Now the second question is, the second part of that question is if they're reducible. Okay, you can see that they're reducible if I can bring them down to a point. If any circuit, a loop can be reduced to a point. Look at this loop here. This loop cannot become a point without actually leaving this region. And same thing here, same thing there. It's not possible. Here, it's not possible to reduce this without a point without actually interfering with the body. This cannot become a point. And obviously, this region cannot become a point. A and B cannot become a point because of the airfoil. However, C can. So the answer is only loop C into the airfoil is reducible. Okay? So now let's go to the next question. The next question says, what's the circulation around the loop C What's the circulation around the loop C for the next two cases. So I'm looking for what is the circulation C in this problem, okay? To do this, I want us to consider the following case. I want you to consider the case where I can have, I'm going to take this and I'm going to cut the donut right in half right there in the cross section, and let me see what happens in the cross section itself, okay? So this is the circulation C. This is uh, uh, B, C, and D. Those are the circulations around this. Now, I could have a big circulation D around all of this, okay, that joins all of these together, because whatever happens outside the loop C can be reducible, okay? So what I know in this problem then is my loop D actually is going to equal to my loop A plus my loop B plus my loop C. And if you think about this, if I have this big loop around this, right, the circulation around that big loop will actually be zero, okay? And because this will be reducible. Let me explain why. Think I have this loop here, okay? And now I am going to bring this loop inside here and I'm going to bring it around there, okay? So this is actually out here, but I'm going to expand it around this, going to a three-dimensional space and go here and bring it around this. That's possible to do. And I can also reduce this to a point. So in that particular case, this is a three-dimensional loop, so I can reduce it, okay? So in this case, I can say my circulation in C will be minus A minus circulation in B, okay? So now we go to the next case scenario. In this case scenario, we also want the circulation. What's the value of the circulation C around this segment? Okay. So to do this, okay. So I want to know what's the circulation C. So in this particular problem, what you can see immediately is that my loop C and my new loop that I put around these two, my loop C and D, they are equal because they are reconcilable. Okay? Because I can actually, without interfering with this one, I can join these together. And we know now that this is actually going to equal to the loop A plus the circulation in loop B. Okay, it's equal to this plus this. So in other words, in this problem, I can say C then is actually equal to loop A plus my loop B. Okay, is the summation of each one of those circulations. Okay, so far so good. So then the next question is, in this airfoil, I want to find what's the value of the circulation at B given this circulation. So I wanted to see this very carefully. So I wanted to see that this loop that's going in this direction here in A, okay, let's call this loop has in A, let's suppose has a velocity dot product uh, my ds vector ds, right? So now this loop here, actually what I can do is I can go this loop and break it down here and keep on bringing this loop here around this, right? So now it's doing this, it's doing this. So it's going in this direction, it's going in this direction. So now what you see is you're going to have your big loop, okay? And so what you can see is I have a loop B, okay? But that loop B, I can actually reduce it just around this as well, right? Because I can make that loop as whatever I want it to be. But that loop B will be nothing else, if you look at it carefully, Okay, watch this. Is this loop right here that we know there's a circulation in A, but I have another one coming in the same direction, just around this loop. So that would be another A. Okay, so in other words, the value of my circulation at B will be 2 times the value of my circulation in A. Okay, that's how we find and we determine these circulations. Now, the last question is a little bit quite interesting because that equation is basically what it's saying is, now let's assume I want you to find this potential. So what is the value of this potential at P? What are the possible values for this potential? So this potential can have n values probably. And then what I know is that the circulation around A is equal to 2. The circulation around B is equal to 3. And the value of my potential at this point, at the initial value, let's call it sub 0, at P, that's going to be value of 1. And you want the smallest values, okay? To do this, this is what we're going to do. So, okay, so I want you to look at this. I'm going to check this, okay? And I can somehow express this whole loop here, the loop C, I can express it like this. And what should be clear here now is, if I have this loop coming in this direction, because it has to be, I cannot have additional circulation necessarily, this one has to go in the opposite direction, right? That's just basically, that's the basics. So what I want you to see now is that my total potential at P, okay, would be the value that I have at P initially, plus, now I can do this loop. How many times I can do this loop? I can do this infinite number of times, n times probably. Okay, and then this loop is going to go around this circle right here, and these are reconcilable. So therefore, I can say the loop at B, right, dot S, and then this one, remember, we always take counterclockwise positive, and then we take clockwise negative. So this will be A dot ds. So this is at A, this is dot ds. And if you realize, this is nothing else than your circulation, and this is nothing else than your circulation. And the problem actually gave me values, right? So this is the value is 1, n, and the value here was 3. This value was 2. So the value is 1 plus n. So the possible values this can have, if I'm going to give you the smallest values of this potential, well, the smallest values of this potential then is going to have all these possible values. It can have 1 when n is 0, can have 2, can have 3, can have 4, and so on and so forth. Okay? So this is how actually we work with the basics of potential flow to understand the basic concepts. This concludes example number 2.